What if I told you that in the next few minutes, you're going to get a superpower? Seriously. It's the ability to see the invisible world of forces all around us, the pushes and pulls that dictate everything from how a planet orbits to why your phone is sitting right where you left it.
I mean, think about it. It seems obvious, right? But what's really going on? There's nothing you can see holding that book up, but it doesn't move. This simple little question is the perfect starting point for learning how to see the invisible.
So here's our plan. First, we'll learn how to actually see these forces. Then, we'll learn the language they speak. After that, we'll figure out the difference between forces in a stalemate and forces that are making a big move. And finally, we'll put it all into action. Okay, let's dive right in.
So the biggest problem with forces is pretty obvious. You can't see them. They're everywhere, but they're totally invisible. So how on earth do we study them? Well, we draw them. We make a simple but really powerful map called a force diagram, which turns all those invisible pushes and pulls into something we can actually look at and understand.
Now, every good map needs a key, a way to read it. And for our force diagrams, the language is all about arrows. It's a super simple visual language, and once you learn the rules, you can read any situation. So let's get into how these arrows work. So what exactly is a force diagram? At its heart, it's just a simple sketch. It strips away all the distracting details and uses arrows to show every single push and pull that's happening to an object. That's it.
And this is what's so cool. One little arrow tells you two crucial things. First, the direction it's pointing tells you, well, the direction of the force, and second, its length tells you its strength. A really long arrow means a really strong force. A tiny little arrow means a weaker force. Simple, but incredibly powerful.
And actually making one of these, it's as easy as 1, 2, 3. Seriously. First, just draw a box or a circle for your object. Second, stop and think, what's pushing or pulling on this thing? Gravity, friction, a person? And third, you just draw one arrow for each of those forces, starting from the center of your object. You're done.
Okay, so now we know the language. Let's see what it can tell us. The first thing we can see is a situation that's kind of like a perfect game of tug-of-war. You know, when both teams are pulling with the exact same strength, just in opposite directions? What happens? Nothing. It's a total stalemate.
In physics, we call that stalemate balanced forces. The two key ingredients are right there. The forces are equal in strength, and they're pulling in opposite directions. Because of that, they just completely cancel each other out.
So the big takeaway for balanced forces is this: no change in motion. That's the rule. If an object is sitting still, it's going to keep sitting still. Everything is in equilibrium.
But come on, how often is a tug-of-war a perfect tie? What happens when one side starts to pull a little harder? Well, that's when things start to move. That's when the action happens.
And this is where we get unbalanced forces. When one force is bigger than the one opposing it, they don't cancel out anymore. There's a leftover force, a net force. And that leftover force is what causes a change in motion. It makes things speed up, slow down, or change direction. We call that change acceleration. This chart just lays it out perfectly. Look at the arrows. If they're equal and opposite, the forces are balanced and there's no change. But if those arrows are different sizes, the forces are unbalanced and you know something is about to change. It's like a visual cheat sheet for predicting what's going to happen.
All right, enough theory. We've got the tool, we know the rules. Let's put this superpower to the test and see how it works with some everyday stuff.
Let's circle all the way back to that book on the table. So what forces are actually happening here? Well, you've got gravity, which is always pulling the book down. But at the same time, the table is pushing back up with an equal amount of force. That's the normal force, and it's literally what stops things from falling through other things.
So when we draw our diagram, what do we see? One arrow pointing down for gravity and another arrow of the exact same length pointing up for the table. The forces are perfectly balanced, and the result? No change in motion. The book stays put. Mystery solved. See? Okay, let's try something more dynamic. Imagine you're pushing a heavy box across the floor. You're applying a force, pushing it to the right. But the floor is fighting you with friction, which is a force pushing back to the left. Now, if you're pushing hard enough, your push arrow is going to be longer than that little friction arrow. And since your push arrow is longer, the forces are unbalanced. There's a clear winner in this tug of war. So what happens when forces are unbalanced? Change. The box starts to move and accelerates across the floor. Okay, last example, a car. The engine creates a forward force. We call that thrust. But at the same time, friction from the road and air resistance are creating a backward force, a drag.
How these two forces relate to each other determines everything the card does.
And this is where force diagrams become so powerful. If the thrust from the engine perfectly matches the drag from friction, the forces are balanced. The car doesn't speed up or slow down, it just cruises at a constant speed. But if the thrust is greater than the drag, the forces are unbalanced and the car accelerates. And if you take your foot off the gas and the thrust becomes less than the drag, the forces are unbalanced again and the car slows down.
And that's the magic trick right there. This isn't just about drawing arrows. It's about looking at a real situation, translating it into a simple diagram, and using that diagram to predict the future, to know exactly what's going to happen to that object's motion.
So now you have this superpower. You can see the invisible. So let me leave you with a final thought to play with. A rocket sitting on the launch pad, about to blast off. What does its force diagram look like? Are those forces balanced, or are they very, very unbalanced?
Pretty cool to visualize, right?